Is our third practice problem for grade 11 Euclidean geometry. We are given a 9.2 that says in the diagram FH is a diameter. So here is FH. Remember your theorem related to a diameter. It says the angle subtended by a diameter on the circumference of the circle is 90 degrees. So this angle, which we can call FCH, is 90 degrees. Just bear in mind, maybe later on we need to use that. So with the center O, so O is the center, FC is a chord, here is the chord FC, and LCH is a secant, so LCH. Now the term secant, it's a line that they don't often mention in Euclidean geometry, but most of the time we have these lines. What a secant is, it goes from one end of the circumference to the other, and it actually goes beyond the circle. So the difference between a chord and a secant is that the chord goes from one end of the circumference to the other, but it does not pass through the circle. The secant here goes through the circle and it actually exits the circle. So notice the LC part here is outside the circle. That's what makes it a secant. E is a point on CH such that CE is equal to HE. So here we have two lines that are equal to each other in length, CE and HE, and that is also indicated by those symbols where they show you that the lines are equal to each other. Now, before I even read the question, one thing I do want to point out here is that it does look like we have parallel lines, but they haven't explicitly told you that the lines are parallel, so we cannot assume. Okay? So 9.2.1, that's actually what we need to get. We need to prove that FC is parallel to OE. So here we have FC and OE, and we need to prove that these two lines are parallel to each other. Now, especially when we need to prove lines being parallel, we try to use something from fun X. Remember fun X, where we have corresponding angles when it forms the F shape, co-interior angles would be the U shape, and alternate angles would be the N or the Z shape. Now, there's many different ways that you can do this, but here is how I'm going to go about working with this. So remember, those are the two lines that need to be parallel to each other. I want to go about proving that they are parallel by making use of corresponding angles. Okay? So to make use of corresponding angles, I'm going to show you that you were told that you have this diameter. And I had mentioned previously that the angle subtended by a diameter on the circumference of the circle is 90 degrees. So this angle, which we can call FCH, is 90 degrees. Let's start off by mentioning that. That we're going to say angle in a semicircle as our reason. Now, since I want to use fun X, here is the F shape that I'm trying to get. If I need to prove that FC and OE are parallel to each other, I can create this F shape. And what do we know about corresponding angles? They must be equal to each other. Right now I've shown that FCH is 90 degrees. If I can show that this angle, which is OEH, is 90 degrees as well, then I've proven that these two lines are parallel because of corresponding angles. So to get this angle, which is E2, as 90 degrees, we notice something from grade 11 theorems. We've got a line drawn from the center of the circle. It has bisected the chord, so notice that chord CH is bisected. Now we have CE and EH that are equal to each other. So it cut the chord in half. It has bisected the chord, so surely it is perpendicular to it. Remember your theorem, perpendicular bisector? That proves that E2 is 90 degrees here. So we're now going to say angle E2 is 90 degrees. We've got that from perpendicular bisector. And now that these two angles are equal to each other, FCH is equal to E2, we have now proven that these two lines, FC and OE, are parallel to each other because of corresponding angles. Just to show you again, here is the F shape, and we've proven that these two angles are equal to each other. So we're going to conclude and say, therefore, FC is parallel to OE, and our reason for saying this is corresponding angles. Now here's the thing, when it comes to questions like this where you are asked to prove something, the main reason that you use to prove is the last thing that you write. You cannot at the start say corresponding angles because you have not yet proven that the lines are parallel. So only once you've shown that they are parallel, then you can say corresponding angles, like what I've done here. Now we are on to 9.2.2, and 9.2.2 says prove that OFLE is a cyclic quadrilateral. Let's find that. OFLE. So we need to show that that shape is a cyclic quadrilateral. Now what makes a quadrilateral cyclic? Remember that there are three ways of doing this. So this is really important for you to take note of. For you to prove that a quadrilateral is cyclic, there are three ways that this can be done. So you could show that the opposite angles are supplementary. You could show that the exterior angle is equal to the interior opposite angle. Or if those two fail, you can prove angles in the same segment. Now it is up to you which proof or which method you want to use, but I would always suggest go with the one that's obvious. If we look at our diagram, what we realize is that we've got this E2, which we proved as 90 degrees. So that forms part of the exterior angle of the cyclic quad. If I am able to show our interior opposite, which will be angle F, the whole of angle F, if I'm able to prove that angle F is 90 as well, then I've proven exterior angle is equal to interior opposite. So it would be a cyclic quad. That's what I'm going to go with. If you want to use any other method, if you want to show that opposite angles are supplementary, you're welcome to do that as well. I would prefer to go with the one that's obvious, basically the one that you have the most information for. So the least amount of working out to get to the answer. Now, just to be able to see this a little better, this is what I am saying. E2 is part of the exterior angle, which is going to equal to the interior opposite. So we need to find a way here to prove that angle F, which I think we should call LFH, makes more sense, or you can call it LFO. Let's go with LFO since we are working with this quadrilateral. If you're able to prove that angle LFO is 90 degrees as well, then we've proven that it's a cyclic quad. So to do this, I want you guys to notice that OF is a radius and FL is a tangent. We've got a radius and we have a tangent. There is a theorem about this which tells you the angle between a tangent and a radius at its point of contact is 90 degrees. Now previously this was known as tan rad, but in recent years the reason has changed to rad perpendicular tan. But basically that is the theorem that we're going to use. So we can say that angle LFO is 90 degrees. And our reason for saying this is rad perpendicular tan. Now from here, we're able to see that angle E2 and angle LFO is 90 degrees. So let's just write this better. There's LFO, which is 90 degrees. So let's say that angle E2 is equal to LFO, which is 90. Now, seeing that we have those two angles equal, we can conclude and say, therefore, OFLE is a cyclic quad. And what have we used to prove this? We've proved the exterior angle of a cyclic quad is equal to the interior opposite. So when you write down your reason, write your reason according to the theorem that you used. Okay, so we have proven that this quadrilateral is cyclic. Now we've got 9.2.3, which says if angle F1 is equal to x. Let's find that on the diagram. So here is angle F1, which is x. We can see that. Express angle O1 with reasons in terms of x. So we need to get angle O1 in terms of x. Now you guys need to notice something. When we look at angle F1, this angle lies between the tangent and between the chord FC. So you guys, this is actually the tan chord theorem that we're going to use. And the theorem says that the angle between a tangent and a chord at its point of contact is equal to the angle subtended by the chord on the circumference of the circle. So angle H is actually equal to x because of the tan chord theorem. Okay, so here angle H is equal to x because of the tan chord theorem. Let's actually start off by writing that down. Now the question that you may have is, how does getting angle H help us to get O1? What you're now going to realize is that points F and C subtended to H, which is on the circumference. Points F and C also subtend to O1, which is at the center. So angle at the center we know is equal to 2 times the angle at the circumference, meaning that angle O1 would be 2x. Okay, and even if you follow with your fingers, you'd notice that FC subtends to H on the circumference, FC subtends to O1 at the center. Angle at center is 2 times angle at the circumference. So now we can add on that angle O1 is equal to 2x. This is angle at center. So that's it. We needed to get the size of angle O1 in terms of x. Please remember to like, subscribe, and turn on your notifications for more content.